All right, it has been a while since I last posted anything, but been busy, so hopefully a lot of things will be coming out in the future, in the near future. I have several projects that are completing and things that should hopefully make for some very interesting discussions. Uh, but for now, I did want to break my streak of silence for now. I think more than a month. And so uh, today's going to be a short and simple discussion, but something that we haven't discussed before, or an application that we haven't discussed before, which is um, quantum autoencoders. So it's another example of a quantum version of a classical machine learning technique. Autoencoders are pretty old. There's papers all the way back in like early 2010s for neural networks, um, or like well-established papers. I mean, there's papers way back about them, but um, they're a technique to transform data into some sort of latent space that is smaller than the dimensionality of the data, and then recover it. So in a traditional neural network sense, you'll have um, your little layers. Actually, I don't want to draw circles. I'll say you'll have your layers that then go down to this latent space, which is then expanded to recreate. So if you have some input, right? You have some example input. This goes down to some, we'll call this a, it's in the, some matrix in the real number plane or space. This is some smaller space. We can call it m by m, where m is less than n. And the exact shrinkage of this information is not strictly required, but that's the idea. And there's a lot of techniques to improve this. A very famous, well-known one is called variational autoencoders, VAEs, which is like a you'll see there's a lot in like generative approaches, although they aren't often as opposed to generative adversarial networks. They don't have a lot of the fine grainedness that a lot of the GANs do when generating like images, because they are often very single modal, I guess. And the fact that from this space, right, you're only going to get a limited sort of set of possibilities. And so, yeah, I mean, there's a whole thing you can read about the mode collapse and stuff of this, but of classical comparisons of autoencoders and GANs. But for now, all that matters is that this concept is sort of simple, and keep in mind this is an unsupervised concept. There's no label, right? We have this input information, then we have this output, right? And now we're comparing. I should call this x hat. We're comparing our loss function based on the actual input and the provided input, and this can be anything, but it might be some just error between the two, and some sort of similarity metric, right? And so we can just do in neural networks and in quantum example, we can just do gradient descent through this for our given loss function. So that's sort of the classical version. The quantum version is very similar. Given some input state here, which goes into our encoder, which I will call U sub E theta, we then go into some latent space, smaller number of qubits, which is some Hilbert space, right? Instead of being real this time, we're just in some complex, I don't know, they use fancy H's to represent this Hilbert space in this complex, which is once again m by m, whereas this is n by n, where m is less than n. And then once again, we increase this. You'll often see these as being measured. It doesn't really matter. I mean, they can be measured, but you're sort of just discarding them, right? You're just saying the information is here. I'm never looking at these qubits again. There's no consideration of them. They're sort of thrown out. And so then, but you can measure them because that resets them before using them again, right? If you only have 10 qubits, you don't want to waste any before this is done. And now this is, we want to make sure that our input state is approximately our output state. And so, by the way, this stands for encoder and this stands for decoder. And I'll be sure to link the famous paper Quantum Autoencoders for Efficient Compression of Quantum Data from 2017. I'll also link another more recent one, which uses some ideas from the data re-uploading paper for some classical data sets for this approach. But with respect to this example that we're working with here, we're going to be working with some quantum data sets. So we consider some input state, this wave function here. We're going to be working with the example quantum data sets of a 1D transverse Ising, which is, and these are already built in TensorFlow-Quantum. We don't need to do anything, so we just have some Hamiltonian, right, which is the sum of this over each of the qubits, right? It's 1 minus g. That's the Hamiltonian. So what this looks like, right, is for a given operation, right? This is like the ZZ operation right here. So we have some power, there's usually some power operation that we're doing, but essentially we're saying, okay, this one, if we have imagine some connectivity to our, I'm going to imagine it as a little grid right here. So these are our qubits. You'll often see them just like this. Then I and I plus 1, actually, I will just leave it as 4. So then there's a connection here, a connection here, and a connection here, right? So I and I plus 1, and then a connection here. And then there's some x on each of them multiplied by some constant, and that's the basic idea of what that Hamiltonian actually looks like in the qubit state. And then we also consider a more complex one, the XXZ chain, which is just Hamiltonian, which has this is I'm just going to write the operations x, I plus 1, instead of writing the little sigma, and this is x. I honestly don't know why it's really called the XXZ chain. Seems like it should be called the XYZ chain, because this next one is y, I plus 1. But maybe I just don't understand the nomenclature. But, it seems like XYZ, but, and then there's some constant here, G, for each of these. And so, yeah, that's the basic idea of it. But the important things aren't that what these mean or why we would care about them, just that this is some quantum data that is at least relevant to something. And so this is some examples. Oh, we're also going to be doing an excited state, which is just applies a circ, like why did I say circuit, an X gate on the qubit. And so it's either excited with an X gate or not excited without an X gate. And so that's basically the idea. And that's a trivial sort of data set. So with the data sets established, right now we can get into the discussion of the quantum autoencoder. So we have our, Hamiltonian, we have our input, we have our, typical parametrized layers that go down here. We have more parametrized layers, and then we have our approximate Hamiltonian. And the way we're going to compute the comparisons is we're just going to take the fidelity of these states, which since these are pure states, since we're operating in a noiseless environment, this is simply the inner product of these states squared. And so that's pretty straightforward. In fact, you can't use channels currently in TensorFlow-Quantum's fidelity generation or fidelity operation. At the last meeting, we discussed adding that, but as of yet, cannot use any noisy stuff in the fidelity op. That being said, you could use some sort of swap test or something to evaluate the fidelity. But using the perfect, math ops fidelity function doesn't work with noisy operations. So with that basic idea established, we can get into the code. And the goal, right, is we have a data set here. We have some unlabeled data set. We're going to encode it. We're going to have testing too. We're going to split into training and testing. And we're going to evaluate on average how good it is at compressing this information down into some subset of qubits, right? So then we could use, presumably, right, if we could effectively compress this data with, 0.99 fidelity, what that really means is that enough information is in these few qubits to be effectively utilized for the full state. What that means is that this could then be plugged into some other algorithm rather than using the full state. So there's the potential to sort of reduce this sort of example. So that's sort of the common approach. There's sort of two maybe uses for this, right? Is that one, you could use it as a generative model. You could create some random latent space and generate an example from that latent space that we or non-randomly, I guess it could be however you want to do it. And then that would generate some sort of fake data. And then, or you could use real data, convert it to latent space, and then use that latent space for something, for example, plugging into another algorithm if it's an effective encoder. So we can just get right into it now. Do that, do this. Got the code right on up. Let me zoom in a little. There we go. We have all the typical imports. Each layer of the parametrized circuit is the same on the encoder and decoder. It's entangled with C0s, and it's just the RY/RZ parametrized gates. Oh my God, that's embarrassing right there. I need to fix something real quick. All right, the problem was just that these were indexed to the same parameter, but that doesn't matter. I fixed that with a simple +1. So basically each layer is C0s and then RY and RZs on each qubit. To make the circuit, we have to have our encoding and decoding params, which this is actually, I can actually fix this. All right, I just realized that there was only really a need for one depth parameter, but that's fine. So we create the encoder and decoder, and before I go too much further into code, I should show how we're going to implement this, right? Because in Circ you have this what's called a reset op, which just puts the qubit to state 0, which is effectively the same as measuring it in our purpose of disregarding the qubit so that we can reuse it, right? So if we have a set of, a set of them right here, then what we can do is just modify them at this point so that we don't have to deal with the reuse of them, which means that it's more efficient to run the algorithm this way. However, the problem is that in TensorFlow-Quantum, at least, the reset op, right? So if we have this little, encoder decoder with the latent space here, we would want to reuse these qubits right here. However, you'd have to reset them and then reuse them. So because you can't use the reset channel or any channel at all, because that's sort of how noise is interpreted in TensorFlow-Quantum, you can't reuse these qubits. And you can't, I don't think they've made this change in Circ yet. I know Qiskit added it, but I don't think Circ has where you can measure. You can do mid-circuit measurements and then do other things. But in terms of TensorFlow-Quantum, it's definitely not allowed. So we have to sort of utilize unnecessary or additional qubits. And what we do is we sort of picture it like this. We have our encoder here that has these, has 3 up here, right? And so we have to use these extra qubits here and here to effectively write this code. And so that's what you're going to see, is rather than this sort of picture where these qubits are reset and refed into the algorithm, we're going to use new qubits because the reset channel is a non-unitary operation and thus isn't supported by the fidelity op, which only works with adjoint differentiation. So with that out of the way, I guess we can move on to the example. And then to modify the states, because we need, so all of these examples can be made for like 4, 10, 16 qubit states. I just work with the 4 because they're the fastest in every scenario. But if we have, right, a latent space of a single, if our latent space is singular and the dimensionality of the Hilbert space, then when we're comparing the fidelity of these states, it's going to error out and get mad at us because we don't have, the state size isn't the same, right? We're comparing the end of the output, which is the latent space plus the original size, and the input, which is just 4 qubits, right? So if we go back to it, it would get mad at us because we're trying to compare fidelity of a state that's this big with a fidelity of a state that's this big, and it's like, hey, you can't compute the fidelities, those states are too different. And so what we do is we basically just do I operations down here, and keep in mind that these states go through and they're the exact they're unmodified in this area. So just keep that in mind. So that's just the implementation detail. But I also just realized this isn't exactly, as soon as I drew this diagram, I was like, wait, this isn't really what we want to be doing now, is it? Because what's happening here is we're comparing this input circuit, which is essentially the input Hamiltonian plus a bunch of 0 states, or product with however you want to draw it. And then this operation, right, is just going to do nothing because it wants these states to be the same and it wants these to also be the same, which means that these operations, which means what it wants to learn, right, would be to have like just undo the C naught operations. So that's not really learning what we would want it to learn, which means I'm going to have to. Okay, well, long story short, that's clearly not what we wanted. I mean, this is going to be instant in the recording, but it's been about an hour real time or something. That's not what we want. That's an implementation flaw. I'll still just super quickly go over to code because it might be useful and I'll share it. But I did implement the correct version of it. So this idea, which is much more similar to the 2017 paper, basically has us do this. So we have our input state right here that goes into our encoder, which has this shared state. We then have our decoder, which goes here. We then do, so we have more qubits here. We then do a swap test with another input state. So these are the same right here to determine swap to determine the fidelity of the states, and then we try to maximize that fidelity. And so this is exactly figure 4 in the paper, the Romero paper, Quantum Autoencoders for Efficient Compression of Data. So that's the idea now. So that requires even more qubits, however, because so in the case where the input has 4 qubits, right? So this is 4 qubits, however many here. This is more qubits. This is the state minus, this is 4 minus latent space qubits. This is 4 more qubits, and this is 1 qubit. So you can see there's quite a few steps to this whole procedure. And this right here, throughout all of this, this is the latent space. These qubits are at this point, right? This is where you would say, okay, I'm going to do something with it. When in the training process, you would do something with it right here. You could do something right here, right? You impress it, you can decode it, right? So this state right here should be approximately that. That's the goal. So it goes from this input small to that, which is big. So that's basically what I just did. So now to give a cursory overview of what you shouldn't do, we can see here, 1 second. There we go. I didn't that. We can see here, right, that we have to use the fidelity operation, convert everything into tensors. We evaluate the fidelity, the sort of buffed up fidelity, and then we minimize that cost. And so this is not what you want to do. I'm still going to upload this code because it might be useful, but what this is really doing, right, is what I previously discussed, which is sort of minimizing this fidelity, which is not at all what we're trying to, not the goal of this problem. This is more like the goal, right? We want this recovered state to be as close to the input state as possible, given only information from the latent space, whereas this is just not it. So now if we actually go back to what we want, it's actually even simpler. So the same layer is defined. It's the exact same. This is all the same too, except now we have a swap qubit and the reference qubits. So we do a swap test. So this right here is the swap test. And I've talked about the swap test in one of the QOSF videos before. So you can check that out. I don't remember which one I want to say it's the first or the second one, but if you don't know what the swap test is, I recommend you check that out. So looking at this, we have to do controlled gate in this format because when TFQ tries to serialize the C-swap gate, it goes to the Fredkin gate, and it gets mad at you for trying to serialize this because that's not in the allowed gates. But this works completely fine. It's the same principle. So yeah, we do the Hadamard gate on the swap test qubit. We do a controlled gate between all possible pairs of the, a controlled swap between all possible pairs of the qubits between the reference state and the decoded state. And then we do another Hadamard on the swap qubit, and that's the goal right there that we want this to be 1, because if this is 1, that means that the states are the same. And so, yeah, anyway, what we're looking at now is the code that's somewhat similar. So given some state qubits, we define how many the size of our latent space. The total qubits, right, is the number of state qubits plus the difference in these two, because that's how many extras we need. We create the qubits, so we have the total qubits here. We add 1 for the swap test qubit, and we need more state qubits because this is the reference state that we're creating. We import our data set, we get our reference data set. So this is going to be the input into the parametrized circuit. This is going to be the comparison with the output of the decoded circuit. We shuffle them all up. We define the number of layers for our model, how many parameters, what the params look like. To format the circuit, we split into training and testing. We do a 90-10 split here. So we split those all up. And then we can, what we can do from here is we can, hold on. Yeah, so what we can see here is that we're splitting the training inputs into training and testing, reference training, reference testing. And then we just combine those circuits, right? Because we're feeding them all into the same input. So what I'm going to do here is now I'm going to print this output, make it nice, hopefully nice and clear. So if I do this, before we continue on, we will be able to hopefully make it clear what's going on here. So the first one that we see here, this is without the reference circuits or the input circuit. So we have a single layer of the encoder, a single layer of the decoder, and here's the shared qubit, right? And so now these 4 qubits are the output states from the decoder. These 4 qubits are the reference states that will be provided, and then this qubit is the swap test qubit. So we only care about looking at this output. This is the full circuit that we're optimizing here. We have this input here, so this is what we care about. We have the input, which is this excited state. We have the reference, which is this excited state. We pass into parametrized gates, and then we do the swap test to each of these. This is just the input, so we can see a big gap between these two, but this is the idea that we can see these two are just these two. And so this is the full circuit. Hopefully this clarifies sort of what I'm sort of talking about here with all these different moving parts. But this is the train circuit, this is the reference circuit, this is the encoder, this is the decoder, this is the swap test qubit, and this is the swap test itself. So hopefully that clarifies all the moving parts. We'll get back into the code. It's pretty straightforward from here on. So now I can get rid of that. I can do that. We create the circuit as I just did. The readout operator is just the swap test one. We create our standard format for TFQ, a string-based input, a parameterized quantum layer with the readout operator and the circuit. We're using adjoint differentiation for speed. We create the model, we use mean average error. So the target, right, is 1 fidelity. So we're minimizing the distance between the output and the 1 perfect fidelity. The optimizer is atom, just with the learning rate. We have early stopping on the validation. We convert the testing and training circuits to tensors. We say the goals are to be all ones, right? For everything, we want 1 fidelity. And then we fit it and we plot the results. So now let's look at some examples. So if I do, this is the simplest example, but it will show something important. This is the excited cluster states, which is basically just, is there an X gate? So it's very simple, but you'll notice something important, and this is a common trend with autoencoders, and it's something I don't know a lot about in the quantum realm. Well, it X'd out pretty early, but you can see here, right, that the training loss is decreasing consistently, or relatively consistently, but the validation loss remains very high. And what we're seeing here is likely what's called memorization. So, also, it could also be because I only have 4 layers. I will now restart that. Sorry, I only had 1 layer. Now I'm adding 4 layers to each encoding and decoding circuit, so that this might help. Yeah, so we can see, okay, that was actually just the problem. Okay, never mind. It's not going to show it here. I guess only if there's a single layer. But what you can see is what's called memorization of the data, where instead of actually encoding and decoding it, it's basically just memorizing it. So that's a common problem in autoencoders that you have to add like regularization for, but we don't see that here. If I go to the back to this data, we can see this is sort of what the output looks like, the plot. Now, if we consider the XXZ chain as the next output, or as the next input, we'll run that code. Maybe we'll see memorization with one of these. All right, there we go. Nope, they seem to be doing pretty well. It might not, it's a common problem in neural networks when you have over parametrization, but that might not be a problem here. So we can see that in the training and testing data, it is effectively compressing the quantum state from the XXZ chain data set into a single qubit from which data is being, extracted into the full state, which is very, very cool, I guess. It's going to keep running for a little while. So I'll just let that run. All right, it is now done. And we can see in the other, and this, what the loss looks like for both testing and training. And sorry, I'll show that for more than 1 second so we can see it achieves very good results. And last, we will do the TFI transverse field icing. And now we will go over here and we will do that. And you can increase the number of qubits for each of these. For example, if I'm going to not run it yet, but I'm going to show what happens if you increase it to, for example, something like, I forget what the next highest, I think it's 8 qubits. Yeah, 8 is the next highest. Well, we'll see if this, yeah, so this is successfully learning pretty well. We'll see when it reaches its end what the graph looks like, and then I'll show you 8 qubits is going to be a lot slower. Keep in mind too, because it requires a lot of qubits to keep track of the whole system. But so let's see. Let's see when this gets done. I will just pause it for now. All right, now that it's finished, we can go on over and show it what it looks like. We can see once again the effectiveness of this autoencoder. Keep in mind the training is, the testing data is not shown in the training, so we can see that it is in fact compressing this quantum data to a single qubit, which is very effective. If you move up to an 8-qubit system and only use 1 qubit as the latent space, it requires simulation of 24 qubits, which is kind of impractical on my laptop, at least in any quick amount of time. But if you use a latent space of 4 qubits, that can decrease the number of total qubits to just 21, which is maybe more feasible depending on your setup. But that's why I don't train any higher order or higher qubit systems. So I know it was kind of weird in the middle. I realized my mistake and wrote a whole bunch of new code, but hopefully this is clear. I'll be sure to link the papers below, but this is what we're looking at here, and this is the final version of what's going on in this code. So hopefully all that is clear. If there's any questions, you can always ask below, and I always answer those. It also has been a while since I made one of these, so yeah, sorry about that, but it's a rocky start maybe, but it'll get better. Yep, that's all.